Welcome! In this session, we'll be exploring the problem number 1673, find the most competitive subsequence. Together, we'll break down the problem, understand its requirements, and work through an effective solution. Let's dive in. In this problem, you are given an integer array called nums and a positive integer k. Your objective is to find the most competitive subsequence of size k from the array. Now, you might be wondering, what exactly is a subsequence? A subsequence is a sequence that can be formed by removing some or no elements from the array without changing the order of the remaining elements. For example, from the array 3, 5, 2, 6, 3, 2, and 5, 6 are valid subsequences, but 5, 3 is not because the order is altered. The term most competitive refers to comparing subsequences lexicographically, meaning the one with a smaller value at the first differing position is considered more competitive. For instance, 1, 3, 4 is more competitive than 1, 3, 5 because, at the third position, 4 is smaller than 5. The input consists of nums, an array of integers, and k, the desired size of the subsequence. The output should be the most competitive subsequence of size k as an integer array. To understand this better, let's take the first example. Here, the input array is nums equals 3, 5, 2, 6, and k equals 2. Our task is to find the most competitive subsequence of size 2. If we list all possible subsequences of size 2, we get 3, 5, 3, 2, 3, 6, 5, 2, 5, 6, and 2, 6. Among these, 2, 6 is the most competitive subsequence because it is lexicographically smallest. This means when comparing these options, 2, 6 comes first in dictionary-like order. So, the output for this example is 2, 6. Let's consider another example to solidify the concept. Here, the input array is nums equals 2, 4, 3, 3, 5, 4, 9, 6, and k equals 4. Our goal is to find the most competitive subsequence of size 4. If we evaluate all possible subsequences of this size, we find that 2, 3, 3, 4 is the lexicographically smallest. This means that when comparing this subsequence with all others, 2, 3, 3, 4 is the most competitive. Therefore, the output in this case is 2, 3, 3, 4. Now, let's look at one more example to ensure the concept is clear. In the final example, we have nums equals 9, 8, 3, 5, 1, and k equals 3. This means we need to find the most competitive subsequence of size 3. After evaluating the subsequences, it turns out that 3, 5, 1 is the most competitive option. This is because it is lexicographically smallest when compared to all other subsequences of size 3 from this array. The constraints of the problem specify that the input size can be very large, up to 100,000 elements, and the solution must operate efficiently in O(n) time complexity. Additionally, edge cases include scenarios like when nums has only one element, where the output is simply the input itself, or when k equals the size of nums, in which case the whole array is the result. Another edge case occurs when all elements in nums are identical, making any subsequence of size k equally competitive. To begin solving this problem, we first consider the brute force approach. The intuition here is straightforward. We generate all possible subsequences of size k from the array nums and select the smallest one in lexicographical order. The steps are simple. First, generate all subsequences of the desired size, and then compare them to find the smallest. However, this method quickly becomes infeasible as the input size grows. The reason lies in its time complexity, which is approximately O(n) to the power of k, in the worst case due to the sheer number of possible subsequences. Additionally, the space complexity is also prohibitive, as we must store all these subsequences during the computation. While this approach is conceptually simple and easy to understand, it suffers from significant computational inefficiencies, especially when n is large, such as 10 to the power of 5. This makes it impractical for real-world scenarios where performance is critical. A more efficient solution relies on a greedy approach using a monotonic stack. The idea is to dynamically build the most competitive subsequence of size k by iterating through the array while maintaining the smallest possible elements in lexicographical order. Here's how this works. As we traverse the array, we use a stack to store elements. Whenever a smaller element is encountered, we check if we can remove elements from the stack while still being able to form a subsequence of size k. This ensures that we continuously refine the stack to maintain the smallest sequence. The key observations driving this approach are that we can discard elements from the stack if doing so results in a smaller lexicographical sequence, as long as there are enough elements left to complete the subsequence. The steps are straightforward: initialize an empty stack, iterate through the array, and push or pop elements based on these rules. Finally, return the first k elements of the stack as the result. This method guarantees that we maintain the relative order of elements while dynamically constructing the optimal subsequence. This greedy approach with a monotonic stack is highly efficient. The time complexity is O(n), where n is the size of the input array, because each element is pushed and popped from the stack at most once. The space complexity is O(k), as the stack only stores up to k elements. These efficiency gains make this approach suitable for large input sizes, such as when n is up to 10 to the power of 5. The trade-offs are minimal. While we do use a stack to maintain the subsequence, the memory overhead is negligible compared to the computational savings. The chosen strategy is clear. The greedy approach with a monotonic stack optimally balances performance and simplicity. By iterating through the array and dynamically maintaining the most competitive subsequence, we avoid the need for backtracking or generating all possible subsequences. The key insight is that we can selectively discard elements while ensuring that we can always construct the required subsequence of size k. This approach is a significant improvement over the brute force method, both in terms of time and space efficiency. This approach offers a robust solution that handles edge cases effectively, such as when n is very large or when there are repeated elements in the input array. It aligns perfectly with the problem's requirements, ensuring that the solution is both efficient and optimal. By leveraging the properties of a monotonic stack, we achieve a balance between simplicity and computational performance. This makes it an ideal choice for solving the problem, even under the most demanding constraints. The strategy ensures that we meet the challenge of finding the most competitive subsequence without unnecessary complexity or overhead. In this problem, we are tasked with finding the lexicographically smallest subsequence of a given size k from an array nums. A subsequence, as you may know, is formed by deleting 0 or more elements from the array while preserving the order of the remaining elements. The challenge here is to ensure that the solution is both correct and efficient, especially when dealing with edge cases. Now, let's start by exploring a brute force approach. The intuition behind this approach is straightforward. We generate every possible subsequence of size k and compare them lexicographically to find the smallest one. The steps are as follows. First, we generate all subsequences of size k. This can be done by iterating through all possible combinations of indices in the array. Python's itertools.combinations is a helpful tool here to enumerate these combinations efficiently. Once we have all the valid subsequences, we compare them lexicographically. For each subsequence, we check if it is smaller than the current smallest one and update accordingly. While this approach is conceptually simple, it is computationally expensive because the number of subsequences grows very quickly as the size of the array increases, making it impractical for larger inputs. The final step in the brute force approach is to return the smallest subsequence we've identified after evaluating all possibilities. However, the time complexity of this approach is a major bottleneck. Generating all combinations involves a factorial growth, specifically O, C, N, K, where C, N, K represents the number of ways to choose k elements from n. For large n, this becomes computationally infeasible. Now, to address these inefficiencies, we turn to an optimized approach that leverages a greedy algorithm. The key insight here is that instead of generating all subsequences, we can maintain a dynamic structure, specifically a stack, to directly construct the smallest subsequence of size k. Here's how it works. We initialize a stack to keep track of our current subsequence, and we calculate the number of elements that can still be removed, which is given by n(k), where n is the size of the array. As we iterate through the elements of nums, we make decisions about whether to include or exclude each element. Specifically, if the top of the stack is greater than the current element and we still have removable elements, we pop the stack to maintain the lexicographical order. This ensures that smaller elements have priority when building our subsequence. Once we've made these adjustments, we push the current element onto the stack. After iterating through the array, we may end up with a stack that contains more than k elements, so the next step is to trim the stack down to exactly k elements, retaining only the first k items. At this point, the stack represents the smallest subsequence we've been constructing throughout the process. Finally, we convert the stack into the resulting subsequence to return as the answer. This optimized approach is highly efficient, as each element in nums is processed exactly once. Each element is pushed onto the stack and, at most, popped once, resulting in a time complexity of O(n). This is a significant improvement compared to the brute force approach, making it suitable for larger input sizes. The use of a stack enables us to dynamically adjust the subsequence in an efficient manner, ensuring that the final result satisfies both the size and lexicographical constraints. There are several key insights that make this optimized approach both effective and efficient. First, the greedy selection process ensures that we maintain the lexicographically smallest sequence at every step. By carefully choosing when to pop elements from the stack, we can avoid the need to generate all possible subsequences. Second, the management of removable underscore elements is crucial. This variable allows us to make informed decisions about when popping from the stack is permissible, ensuring that we always end up with exactly k elements. Finally, the stack operations themselves are highly efficient. The ability to add and remove elements dynamically ensures that we can maintain the desired order and size constraints without additional overhead. These combined factors make the algorithm not only optimal in terms of time complexity but also elegant in its design. To implement this algorithm effectively, we rely on two key data structures. The stack is central to the construction of the subsequence, allowing for O(1) push and pop operations. This ensures that the algorithm remains efficient even for large input sizes. Additionally, variables like removable underscore elements play a critical role in tracking how many elements can still be removed, providing clarity and precision in decision making. It's also important to consider edge cases to ensure robustness. For example, when all elements in the array are equal, as in nums equals 2, 2, 2, 2, with k equals 2, the subsequence would simply be 2, 2. In cases where the array is in strictly decreasing order, such as nums equals 5, 4, 3, 2, 1, with k equals 3, the algorithm correctly pops elements to produce 3, 2, 1. If k equals the size of the array, the entire array is returned as no elements can be removed. Conversely, when k is 1, the smallest single element in the array is returned. By handling these scenarios effectively, the algorithm ensures both correctness and efficiency across a wide range of inputs. This implementation solves LeetCode problem number 1673, find the most competitive subsequence. The goal is to extract the lexicographically smallest subsequence of size k from the given array nums. The function most competitive uses a greedy approach combined with a stack to maintain the most competitive subsequence. 1. Stack initialization. We start with an empty stack, which will hold the elements of the most competitive subsequence. 2. Iterating through the array. We iterate through each number in the input nums. Condition for removal. While the stack is non-empty, the current number is smaller than the top of the stack, and there are enough remaining elements in the array to still construct a subsequence of size k. We pop the top of the stack. This ensures that the stack remains lexicographically smaller when possible. Adding to stack. If the stack has fewer than k elements, we append the current number to the stack. 3. Output. After processing all elements, the stack will contain the most competitive subsequence of size k. Edge cases handled. If nums has exactly k elements, the function directly returns nums as no elements can be removed. The algorithm ensures that the stack does not exceed size k and handles cases where nums contains duplicate or strictly increasing/decreasing values. Complexity. Time complexity, O(n), where n is the length of nums. Each element is pushed or popped from the stack at most once. Space complexity, O(k), where k is the size of the stack, as we only store the most competitive subsequence. This compact yet efficient implementation ensures correctness and optimality for the problem requirements. Here, we begin by importing the necessary libraries and defining our solution class. The main method, most competitive, takes two inputs, an array of integers nums and an integer k, which represents the size of the most competitive subsequence we need to find. To help us efficiently manage the subsequence, we use a stack implemented as a deque. The loop iterates through each element in the nums array. For each number, we check if the stack can be optimized by removing elements. Specifically, we remove elements from the stack if the current number is smaller than the element at the top of the stack, and if there are still enough remaining elements in the array to ensure that we can form a subsequence of size k. This ensures that the stack always holds the smallest possible values while maintaining the required constraints. After the removal process, if the stack size is still less than k, we add the current number to the stack. This ensures that we are building the subsequence incrementally while respecting the size limit. Once the iteration is complete, we need to convert the stack into the resulting array. We initialize an index variable and iterate through each element in the stack, assigning these elements to the result array in order. This process ensures that the stack's contents, which represent the most competitive subsequence, are correctly transferred into the final output. Finally, we return the result array, which contains the desired subsequence of size k. This completes the implementation, with the algorithm ensuring both efficiency and correctness by maintaining the smallest lexicographical order while adhering to the size constraint. In this problem, we are tasked with finding the lexicographically smallest subsequence of length k from an array, while maintaining the relative order of the elements. To solve this, we use a stack-based approach. Let's consider the example where nums is 3, 5, 2, 6, and k is 2. Initially, our stack is empty, and the length of nums is 4. In the first iteration, we encounter the number 3. Since the stack is empty, we append 3 to it, resulting in a stack of 3. In the second iteration, we come across the number 5. Since 5 is greater than the top element of the stack, which is 3, and the stack size is still less than k, we append 5 to the stack. Now, the stack becomes 3, 5. Next, we move to the third iteration with number equal to 2. Here, 2 is less than the top element of the stack, which is 5. Because there are enough elements left in the array to fill the subsequence, we can safely remove 5 from the stack. After popping 5, the stack becomes 3. Now, 2 is still less than the new top of the stack, which is 3, so we remove 3 as well. The stack is now empty. We then append 2, making the stack 2. Finally, in the fourth iteration, number is 6. Since the stack size is still less than k, we append 6, resulting in a final stack of 2, 6. Thus, the most competitive subsequence for this example is 2, 6. In another example, nums is 9, 8, 7, 6, 5, and k is 3. We start with an empty stack and the length of nums is 5. In the first iteration, we encounter the number 9. Since the stack is empty, we append 9 to it, resulting in a stack of 9. In the second iteration, we process the number 8. Here, 8 is less than the top of the stack, which is 9. Because there are enough elements left in the array to complete the subsequence, we pop 9 from the stack. We then append 8, making the stack 8. In the third iteration, number is 7. Since 7 is less than the top of the stack, which is 8, we pop 8 from the stack, leaving it empty. We then append 7, resulting in a stack of 7. In the fourth iteration, number is 6. The stack size is still less than k, so we append 6 to the stack, making it 7, 6. Finally, in the fifth iteration, number is 5. Again, the stack is not yet full, so we append 5, resulting in a final stack of 7, 6, 5. The most competitive subsequence for this example is 7, 6, 5. Now let's consider a more complex example where nums is 2, 4, 3, 3, 5, 4, 9, 6, and k is 4. We start with an empty stack and the length of nums is 8. In the first iteration, number is 2. Since the stack is empty, we append 2, resulting in a stack of 2. In the second iteration, number is 4. The stack size is less than k, so we append 4, making the stack 2, 4. In the third iteration, number is 3. Since 3 is less than the top of the stack, which is 4, and there are enough elements left to complete the subsequence, we pop 4. We then append 3, resulting in a stack of 2, 3. In the fourth iteration, number is 3 again. Since the stack size is still less than k, we simply append 3, making the stack 2, 3, 3. In the fifth iteration, number is 5. The stack still has room, so we append 5, resulting in a stack of 2, 3, 3, 5. For the remaining iterations, we encounter 4, 9, and 6, but we skip these because the stack is already full. Thus, the most competitive subsequence for this example is 2, 3, 3, 5. The time complexity of this solution is O(n), where n represents the length of the input array, nums. The algorithm involves iterating over each element of nums exactly once through an outer loop, which is clearly an O(n) operation. Inside the outer loop, there is also a while loop that removes elements from the stack based on specific conditions. However, each element is pushed onto the stack at most once and popped from the stack at most once during the entire runtime. This means that the total number of stack operations, both push and pop, are bounded by n. As a result, the inner while loop runs an amortized O(1) time for each iteration of the outer loop. When you combine the outer loop with the inner operations, the overall time complexity remains linear, or O(n). This is a key factor in the efficiency of the algorithm. Now let's analyze the space complexity of the solution, which is OK, where k is the size of the resulting subsequence. The primary contributor to space usage is the stack, which is designed to store up to k elements. The algorithm ensures that the size of the stack never exceeds k, so the memory usage of the stack is proportional to k, or OK. Beyond the stack, the additional variables used in the algorithm, such as n, I, and number, along with the input array nums, do not contribute to the space complexity because they either use constant space or are part of the input. Thus, we can confidently conclude that the total space complexity for this solution is OK. To better understand the efficiency of this approach, let's compare it to a naive solution. A brute force method would involve generating all possible subsequences of length k and then selecting the lexicographically smallest one. This would require computing combinations, which has a time complexity of O(n) k or O(n)/k *nk. Since this grows factorially, the naive approach becomes computationally infeasible even for moderately large values of n. In contrast, the optimized solution uses a greedy algorithm combined with a monotonic stack. By processing each element in nums exactly once and limiting stack operations to at most n, the optimized approach achieves a linear time complexity of O(n). This significant improvement makes the greedy, stack-based solution not only feasible but optimal for solving this problem. Finally, let's break down the time complexity into best, average, and worst-case scenarios to reinforce our understanding. In the best case, where the elements in the input array are already in the desired order, such as increasing order, the while loop executes very infrequently, resulting in an O(n) time complexity. For the average case, with randomly distributed elements, the stack may undergo frequent updates, but the amortized efficiency of the inner loop ensures that the overall complexity remains O(n). In the worst-case scenario, where the input array is in decreasing order, every element triggers the while loop to execute. Yet, even in this case, the amortized analysis guarantees that the total number of stack operations does not exceed n, maintaining an O(n) time complexity. The mathematical reasoning behind this lies in the fact that each element is pushed to and popped from the stack at most once, and the outer loop processes each element exactly once. As a result, we achieve an efficient solution with O(n) time complexity and O(k) space complexity, making this approach not only optimal but also highly practical for competitive subsequence problems. When solving this problem, there are some common mistakes to watch out for. First, not accounting for edge cases can lead to incorrect results or failures. Examples include situations where the value of k is greater than the length of the array itself is empty, or all elements in the array are identical. It's critical to validate inputs and handle these cases explicitly. Next, relying on brute force to generate all subsequences of size k can be extremely inefficient. This approach has an exponential time complexity of O(2 to the power of n, which becomes impractical for larger arrays. Another pitfall is misunderstanding lexicographical order. This is not the same as numerical sorting. For instance, the sequence 2, 10 is greater than 2, 3 lexicographically because comparisons are made element by element, similar to how words are ordered in a dictionary. Modifying the input array directly is another issue to avoid, as it can lead to unintended side effects if the array is needed later in its original form. Finally, overcomplicating the solution by introducing unnecessary data structures, like heaps, instead of simpler ones like stacks or queues, can make the implementation harder without providing significant gains in efficiency. Now, let's focus on tips for interviews. Optimizing your solution is key. While brute force shows basic understanding, interviewers generally expect more efficient approaches. For example, a greedy algorithm or stack-based solution often demonstrates a deeper comprehension of the problem. You should also be prepared to discuss trade-offs between time and space complexity. For instance, while a heap-based approach might be slower, it could simplify some aspects of implementation compared to a stack-based method. Understanding lexicographical order is another critical point. Be ready to explain how you determine the correct order and how this is implemented in your programming language of choice. Additionally, demonstrating awareness of edge cases is vital. Clearly explaining how you handle scenarios like empty arrays or large values of k shows thoroughness and helps avoid bugs. There are also several related problems that can help you deepen your understanding of this topic. For instance, LeetCode 3.16, which focuses on removing duplicate letters, and LeetCode 4.02, which involves removing k digits to form the smallest number, share similar concepts. Problems like LeetCode 10.81, where you find the smallest subsequence of distinct characters, and LeetCode 3.21, which requires creating the maximum number, are also worth exploring. As for alternative approaches, the greedy stack-based method is a popular choice. It offers a significant speed advantage with time complexity but requires careful handling of edge cases to maintain the correct stack size and enforce lexicographical order. On the other hand, the heap-based approach simplifies lexicographical comparisons but comes with increased space complexity, typically k log n. This method can be a good fit for problems where pruning is less essential but sorting is important. Finally, dynamic programming is another approach to consider, although it's generally overkill for this specific problem. It's best suited for scenarios where subsequences need to satisfy additional constraints, such as incorporating weights or costs. While dynamic programming can handle more complex requirements, it often comes with higher computational overhead, making it less practical for problems like this one unless the constraints explicitly demand it. Understanding when to apply dynamic programming and when simpler methods will suffice is an important skill to develop. Great job! In this session, we reviewed the problem, understood the brute force approach, and highlighted key takeaways. Remember, practice makes perfect, so keep honing your problem-solving skills. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!